Okay, hello everyone. Welcome to today's AutoML seminar. I'm very happy to have Ganesh Yavahar here today, who was a PhD at the University of British Columbia and is now a research scientist at Google DeepMind. And today he's going to talk about Mixture-of-Supernets. And I'm very happy to have you here today as our speaker and looking forward to your talk.
Yeah, thanks for the introduction. Hi everyone. I'm going to talk about my work, Mixture-of-Supernets, improving weight sharing supernet training with architecture routed mixture of experts. This was some work I did 2 years ago when I was an intern at Meta Reality Labs. So part of this work was done in Meta, and then the rest was done when I was back to my university. So you would see collaborators from both my university and Meta. And this work, I was trying to submit it in many conferences in the last 2 years, and I finally got in ACL 2024 as a findings paper. So I will present this work very soon in ACL. Right. So let's get started with some introduction about certain concepts in neural architecture search. Some of you might already be familiar with them. Starting with weight sharing supernet. So in neural architecture search, one of the biggest problem is to get a performance estimate of an architecture in a search space quickly. So in the search, we usually evaluate so many candidate architectures, and we usually don't have the bandwidth to train each of the architecture from scratch to convergence to get a performance estimate. And we typically need to build some estimation methods that can quickly, give a performance estimate, and that also has some nice, correlation with the ground truth, performance. So one of the popular, estimator in natural language processing, as well as in other fields like computer vision, is to use weight sharing supernet to represent all the weights of all the architectures in the search space. So this example that you're seeing is the weight sharing supernet for a mixture of expert model, encoder decoder model for a machine translation task. And usually we have the search space defined, predefined search space. And the largest model in the search space is usually called as the supernet. And we would extract weights for the subnets by extracting, common, the first, like few rows or columns extraction, right? For example, if the embedding size for the largest model is, let's say, 700, right? And let's say for the subnet that you are interested in, the embedding size is 500. So we'll extract the first 500 features, and we'll say that is the weight of the that's going to be the weight for the subnet, for this embedding layer. And similarly, we can use this notion, extend this notion for other components of transformer model, for example. And this is for the FFN layer. We could have, let's say, like flexible number of input features and the output features. The supernet here has 3072 intermediate FFN intermediate size and 640 as the embedding size. Let's say the subnet has an embedding size of 512 and then the FFN intermediate size of 2048. We will extract the first 512 columns corresponding to the embedding size, and then the first 2048 rows corresponding to the FFN intermediate size. And this sliced, this cropped weight matrix is going to be the FFN initial layer for this subnet model. And we can extend this notion again for the other FFN sublayer, right? So overall, in the training process, we usually sample an architecture from the search space. We extract weights for that architecture and then train that architecture for the task of interest. And then we keep doing that. The hope is that after training, we could sample an architecture during the search and or we don't sample. We usually know what architecture for which we want the performance, and we could extract the weights and then run those weights on the validation set, and we get a performance estimate. And that's usually like a good enough proxy, for ranking the architectures and such. And this recipe has been used to build efficient BERT model, efficient machine translation model. In this work, I'm mostly going to focus on the applications of weight sharing SuperNet for natural language processing, mainly trying to understand the difficulties in adapting the SuperNet for NLP, for building efficient NLP models, and then trying to improve their modeling. Right. So one thing of interest in using SuperNet for NLP is that when you look at the performance of the standalone model, which is training, let's say for an architecture, training that architecture from scratch to convergence using the standalone settings, compared to taking the same architecture after that the SuperNet training is converged, and then comparing the performance with the standalone. Ideally, we don't want any regression. We want the performance estimates to be as close as possible to the standalone performance. But in practice, there is usually a gap, and in the cases that we are going to see today, BERT and machine translation, the gap is quite big. So here you could see for the BERT search space. So I have the performance of the standalone model and then the SuperNet model. And these are some benchmark data set for natural language understanding, the GLUE benchmark. And we could look at the average GLUE. Usually the trends can vary between individual tasks, and average GLUE could be a good enough proxy to see the performance of BERT architecture. So basically here in the search space, we are trying to find a pre-training BERT architecture, which is good enough for like fine-tuning to lead to a good downstream task performance. So you could see that while you look at the last column only, the average GLUE, there is a performance drop of 0.13 points. And this is usually a big drop for GLUE. And so this also indicates that when we do SuperNet training using the standard recipe, there is a regression compared to the standalone performance. And if you also look at machine translation, this is on the popular machine translation benchmarks, English to German, English to French, and English to German different here, right? And HAT is a once for all adaptation, to machine translation settings. So it's using the classic SuperNet training, where in each step it is only going to sample an architecture from the search space. Yeah, and we could have another variant also doing sandwich sampling. So in sandwich sampling, we not only use the randomly sampled architecture, but we also use the largest model and then the smallest model, and we train all the three architectures together at every step. And we see two metrics here. I think for this slide, the first metric is more important, which is the mean absolute error. So this is taking few architectures from the search space, and then trying to get its standalone performance for each one of them, and then the SuperNet performance, and then trying to compute the mean absolute error between them. So lower the better for the SuperNet. And you could see that, I mean, in a way, like the sandwich sampling reduces the gap, but it's still, the overall gap is quite high in terms of the blue point. So for example, 1.6 blue points is really high high room for error. So again, from the machine translation side, also we could see a huge regression by using the Supernet training and trying to compare its performance with standalone. So the goal of this work is to try to address the performance gap. In best case, try to bridge it. At least in worst case, try to minimize the gap as much as possible. So the key motivation also for that kind of effort is that once the SuperNet training is done, and then we go ahead and do the search, and then we get the best architecture. Maybe the SuperNet is good for ranking the architectures. So we, let's say, get good results on the search side, and we get an efficient architecture. Now, the problem is, how do we get the weights for the efficient architecture? There can be two ways to it. One is that once you get the architecture, you throw away your NAS pipeline and you train that architecture from scratch to convergence. In some cases, it could be very expensive. For example, for the BERT case, you have to train a BERT, have to do BERT pre-training from scratch. It can be quite expensive. Or another approach is to use the SuperNet itself to get the final weights for NAS. And in that case, we want the weights to be accurate. So the gap, between the SuperNet with the standalone gap to be minimal, so that we can readily use the weights for the final architecture. In some cases, we might need to fine tune, for a few steps, but at least we should ensure that we are working on some setup that reduces the additional training demand. Because in most cases, what happens is that even in industry, happens that we run neural architecture search for various constraints. Could be on the model size or latency, and on also various devices. So we have like bunch of efficient architecture information, and we want to be able to get the weights, the optimal weights for these architectures also as quickly as possible. So this is in general like the motivation, for why we need to focus on bridging this standalone versus SuperNet performance gap. Right. Yeah. So then we can wonder, what could be, potential reasons why the performance gap is there for the SuperNet. So if you look at the standard SuperNet, if you take a smaller model, I think I showed this before. This is a smaller model. Let's say it uses 512 embedding and then 2048 FFN intermediate size. And you can imagine a bit bigger model, 600 embedding and 2900 FFN intermediate size, right? Here you could see that a smaller model should always be a subset of the bigger model in terms of the extraction process that we are using. Right. So in that sense, what we are seeing is that regardless of the model properties, whether it's a smaller model or a bigger model, the smaller model has to share all its features with the bigger model. That's kind of a strict notion the standard SuperNet has. And that could lead into several issues during the training and even after training, for the performance. Right? It could be some cases where during the training process, the gradients from the smaller model conflicts with the gradients from the bigger model. And in that case, they can cancel out each other's learning and virtually reduce their learning. So it's important to build a framework that has a flexible notion of weight sharing, between architectures, which could also take into account the architecture characteristics into account while sharing the weights, right? So that would be the best if we have some way, where we could say you could use these rows for sharing weights with the SuperNet, and that selection process is taking the subnet architecture information into account, right? So that's one way, and usually in practice, even in papers, in NAS papers, they call this problem the problem where gradients from a smaller model, let's say, conflicts with gradients from larger model as gradient conflict problem, and it's an important challenge to be addressed to train Supernet effectively. And that's one side, or the gradient conflict side. On the second side, the capacity limitation. In general, the search spaces that we use in neural architecture search is extremely huge. The BERT space that we would use in this work is about 7 billion architectures, and the machine translation space is about 6 million architectures. So it's really huge, and we are relying on one single SuperNet model. Just the largest model in the search space, the weights from it, to parameterize numerous architectures in the search space. And that might not be enough. As the search space increases, the problem complexity also increases. The SuperNet, training objective, the complexity of that increases. And we might also want to scale up the SuperNet also accordingly. So in the standard SuperNet setup, we don't have that. Like the architecture is kind of each weight is limited by the number of parameters that it represents. So in this case, it's mostly the features that you see here highlighted, and that could be also be a limiting factor. We might want to have a flexible way to increase the capacity of the subnet while respecting, the subnet architecture information. So these two are, general challenges, and the framework that we are going to see kind of implicitly tries to address them. I think maybe the capacity limitation, you would see that it is explicitly optimizing for it. And we can discuss them in a bit. Yeah. Right. All right. Yeah. So let's start with the motivation for the Mixture-of-Supernet, the framework that we are proposing in this work. We'll start by looking at the standard Supernet training loss, so where we are minimizing for a given weight. So we sample the input and the label from the training data here, and then we sample architecture from the search space here. And then the loss function is specific for the task of interest. Let's say it could be for BERT pre-training, it could be a task agnostic, mask language modeling loss. For machine translation, it could be the standard, the translation loss. Right. Yeah. So the function here is the model function for this architecture A, and takes input X, and the weight corresponds to the SuperNet weights, and we have the label Y, right? So this is what the SuperNet is trying to minimize during its training process. And what we are trying to propose is we are trying to propose a generalized model function G, which also takes A, which is the architecture as input. You could see that a special case of G could be the F model function, and we could see, if how we could leverage this notion by what we get by taking the architecture also into the function, right, that represents the weights for the architecture. So in general, the idea is that to minimize the SuperNet training loss, if we make the function G, which is going to replace the F very soon, as expressive as possible. Let's say one way to make a function expressive is to add more layers, make it more complicated by adding more number of parameters, usually result in smaller loss. This is some kind of an intuitive assumption that we have. And the problem here is that we can't use traditional techniques to increase, to make a function expressive. For example, if we add more layers to make the function G expressive, then it can no longer respect the the original architecture A, right? So we have that kind of a constraint, for making the function G expressive. And so the key idea we had in this work is to define the function G as a mixture of expert routed by the input A. So we remember A is the architecture, and we are basically saying that the architecture is going to um, tell us how we'll implement the function G, right? So this is the general notion of the mixture of supernets, and we kind of instantiate this in two variants. The first one is called layer-wise mixture of supernet. So we are now replacing the function f with g. And in the standard case, let's say we have the input x, and imagine the neural network model has just one layer, and we have one linear layer here. And we would, let's say the flexible hyperparameter in the set space is also the number of output neurons. So the rows are the only ones where that's going to vary. And depending on the number of rows for the subnet, we'll extract that and we'll say that's the weight, right? That's how the traditional F function works. What we are saying here is for the layer-wise mixture of supernet, we will introduce a bunch of weight matrices, not just one. So the number of, you can treat each weight matrix as an expert weight matrix. So we have a bunch of expert weight matrices. They are all going to work in tandem to give us the weight for the architecture of interest for us, right? So that's the whole thing. So this is kind of linked to the idea of mixture of supernets, where we try to maximize the increase the capacity of a model by adding more by duplicating the blocks. Like, and usually, like in mixture of supernets, we also do we typically duplicate the FFN blocks, and once duplicated, each one of them have independent weights, and we try to make use of them. So it's kind of that idea there that we kind of like decompose a single weight matrix into a bunch of different weight matrices. And now we need a mechanism to combine these different weight matrices to arrive at the final weight matrix for the architecture. So that's where we use the router component. This is kind of like similar in concept with the router in the mixture of experts, if you may know. In that, we either use the token embedding or we use the complete sequence embedding as the input. But in this case, there is a big difference there. We use the architecture description as the input. It could be all the moving hyperparameters for the architecture in the search space, and we could just feed it as a feature vector and try to get a probability distribution over all the expert weight matrices we have. The goal of this router is to come up with this probability distribution, one value for each of the weight matrices, such that it's kind of assigning weight to a architecture, taking the architecture characteristics into account. Remember that we saw before that if you have, let's say, smaller model and have a larger model, and usually they have different modeling properties, and we should probably minimize the weight sharing between them. So this is some task the router can take. So taking the architecture, a smaller architecture as input or larger architecture as input, it could generate a very different probability distribution, such that when we take, for example, the smaller architecture, it could say that you can use all the features from the linear one matrix. And for the bigger architecture, it can say that you can use all the features from the linear two weight matrix. So in that sense, you can imagine that there is very less weight sharing between the smaller architecture and then the larger architecture, thanks to the way the router is assigning these probabilities, right? So this is what is like an extreme case we can expect, but usually there is no absolute non-weight sharing between two architectures. There is usually some kind of weight sharing, but at least we have a way to control. And the idea is to learn this weight sharing how to use these matrices also during the SuperNet training process. So once we have the um, once we have these weights, we would use these weights to combine the um, different weight matrices, right? So I think I'm talking about two different weights. I think one is the weight matrix, the other is I can call it as the alignment probabilities, the alignment of an architecture with respect to each weight matrix. We could use them. These are you can imagine as some scalars to do a weighted sum of all these matrices and to arrive at the final matrix. And then we can do the cropping based on the desired number of output neurons. So essentially, at high level, what we are doing is that we are decomposing a single weight matrix into multiple set of weight matrices, and then we are trying to use the architecture as input to the router to guide this process, right? Like guide this weight generation process. Yeah, I think I'm probably like we're running short of time, so I'll go like a little bit fast. So we have other variant of the mixture of supernets, which is neuron-wise mixture of supernet. So in the earlier case, the flexibility was in terms of the number of expert weight matrices, and that's kind of limiting in the sense that if you want to increase the flexibility, you want to increase the number of expert weight matrices, and that's going to introduce large number of parameters. It might make the overall optimization process difficult. So in the neuron-wise MOS, the biggest change is that instead of each weight matrix acting as an expert, here um, um, each neuron will act as an expert. We could treat each output neuron, a row, as acting as an expert, and the router is going to give a probability distribution over all the output neurons across all the expert weight matrices. So you could imagine that the flexibility kind of increases by the number of features, output features times the number of expert weight matrices, right? Yeah. So yeah, compared to layer-wise MOS, you could see more flexibility by going with a neuron-wise MOS. And we'll see the training overhead, in using mixture of SuperNet compared to the standard SuperNet in a bit when we look at the experiments. But the whole idea is that, like going back to the gradient conflict, we know now that we have a way to assign weights, taking the model characteristics into account. So we might be able to control the gradient conflict implicitly. In terms of the capacity limitation, we explicitly set more weight matrices using ideas from mixture of experts, so we can control for that also, right? Yeah. So overall training, so we do sandwich sampling, let's say for the mixture of for the machine translation. So we would sample random architecture and then the biggest model and then the smallest model, and then depending on the type of the mixture of SuperNet, we would extract the weights based on that, and we would compute the loss. Yeah, I think otherwise it's a standard training recipe. It's not much changes. And now let's look at some of the results. So the one claim was that the alignment vector, which is the vector coming out of the router, is kind of taking the architecture properties also into account. So that's one claim we made. So now we can empirically check by looking at the Jensen Shannon distance of these alignment vectors between two different architectures. For example, we can look at the smallest architecture and the largest architecture, and we could compare the distance. And we want the distance to be high. That would indicate that there is like low amount of weight sharing between them, and that's what you see. If you compare the smallest and then the largest architecture, you would see some high distance. And then if you compare the smallest with the smallest, there is like less amount of distance. So there is maximum weight sharing between that. Intuitively, it makes sense that smaller models might have more features to share between them compared to smaller and larger models. So naturally, the alignment vectors are kind of taking that into account, which is good to see across different data sets. And I also mentioned about the gradient conflict, and one commonly used way to measure gradient conflict is to compute the cosine similarity between the supernet gradient and the smallest subnet gradient. And you want the cosine similarity to be high, because if it's low, it means that the gradients from two different models are conflicting with each other. And you could see that with our mixture of supernets, the cosine similarity is becoming very high. That means that we are kind of controlling the gradient conflict implicitly via this architecture specialization, right? Yeah. So now we'll look at, I'll run through all the BERT and machine translation results. So this is the glue performance across different supernets. If you look at the average glue, we not only bridge the gap between the standalone and supernet, we actually improve it significantly. And yeah, and if you look at the overhead also, it's kind of within 22% in terms of training time hours. This is a one-time investment we can do, and after the search, we never need to do any retraining, at least for the BERT case. And we compare also with other state-of-the-art NAS frameworks for BERT, like Autodistil and NASBERT. And NASBERT mainly says that once you do the search, you have to actually train that architecture from scratch to convergence. So you have to execute the entire BERT pre-training pipeline, which can be very expensive. I could see that in our case, you don't do any additional training. Once the supernet training is done, you can actually extract the weights and use it. We could beat the NASBERT, and we also compared to Autodistil. Autodistil uses few shot NAS. It kind of splits the search space into 3 different search spaces and trained 3 different supernets. So kind of like more overhead in maintaining a lot of supernets, unlike our case where we have a single supernet, which kind of like increases the capacity, based on the need, right? Yeah. And for the machine translation side, I think I'm again flashing the same, the standalone versus supernet gap, which I showed before. Could see that we can considerably reduce the gap in terms of the MAE. And in terms of Kendall, the picture is kind of very different. So the Kendall is measuring the ranking performance of the supernet. And could see that the ranking doesn't improve greatly, and it doesn't greatly decrease also. So I think the main benefit that we are getting is in bridging the gap, and not so much on the ranking. But we would see that it's probably hard to say, ranking the Kendall is like a strong correlation to the final performance. We'd see that still our model identifies better architecture and then minimizes the overall training needed, right? So you could see that from the previous slide that the gap is not fully bridged, at least for the machine translation case. So it's kind of like quite a hard task, unlike the BERT. And we want to, do that, right? We actually compare against the state-of-the-art NAS for MT framework, which is hardware-aware transformers. Across different latency constraints, you can see the models from the Pareto friend. The performance is quite high compared to HAT. Hardware-aware transformers again is the once for all, work for machine translation, right? And so since we couldn't close the gap, we could always further fine-tune the final architecture to reach the performance as a standalone. So if it is a supernet, then we need to ensure the number of additional fine-tuning steps are minimized. And we could see that for our supernets, we could enjoy, with a minimal number of additional training steps to close the gap, right? So that's good to have. At least in the worst case, we could now reduce the additional training that is required, right? Yeah. Just to conclude, in this work, we introduced a mixture of supernets, formulation aimed at improving the expressive power of supernets. And we used the idea of MoE to generate flexible weights for the subnets. We did extensive evaluation on BERT and machine translation setting. We could show that we could close the gap for the BERT and then reduce the gap further for the machine translation setting. And for the machine translation setting, we could also minimize the retraining time required. And overall, we could also get higher quality architectures compared to the prior NAS work. Yeah, that's pretty much from my side. And if you are interested in using the code, I just uploaded one in the GitHub. I think I might need to clean it a bit, but yeah, feel free to use it and post any PR request if needed. Yeah, thanks.